Okay, welcome back. So we will continuously to introduce the multi-stage vapor compression refrigeration cycle. I know it's boring. However, I think it's useful. It's because you can implement your technology into related different fields. And then let's have a look. So our first example for the multi-stage vapor compression system is the compressors connected in series. So if it's in series, connected in series, so we can see we can split the high pressure ratio into 2 stages, okay, or even maybe more stages. And also, however, so because due to the higher compression ratio, there's the high which will result in high discharge temperature. So therefore, we will end intercooler to cool down the high discharge temperature after the first stage compression. So then, in fact, in engineering practice, we still have the compressors. We can see 2 compressors connected in parallel. It's wrong, okay? Parallel. So the compressors connected in parallel. So now let's have a look. It's called Cascade refrigeration system. So now let's have a look. Because as I have mentioned, if the evaporating temperature is much lower than the condensation temperature, maybe we need multi-stage compressors. So the compressors can be connected in series, just like previously introduced, and they also can be connected in parallel. So if they connected in parallel, let's reintroduce. Okay, so firstly, we can see there are 2 stages of compressors. Okay, there is we can see it's low, maybe we call low pressure compressor and high pressure compressor. High pressure compressor and low pressure compressor. Okay, we have 2 stages of compressors. So, and they are connected in parallel. So with only just like we remember the like forward heat engines in series. Okay, so between them, okay, so the interaction, the link of the 2 loops are the cascade condenser. So so we can see this condenser in fact serves condenser So we can see, in fact, it serves as a condenser, low pressure loop, serves as low pressure loop condenser. However, for the high pressure loop, it serves as a evaporator. Okay, evaporator. So there is no direct contact of the working fluids in the two loops. So we can see for this one, although we have two-stage compressors, they connected in parallel, and for this two-stage cascade refrigeration system, so we can see besides we have a cascade condenser. In fact, it serves as the low pressure loop condenser, but it also serves as the high pressure loop evaporator. And there is no direct contact between the working fluids in the two loops. So there's no direct contact. So therefore, the working fluid can be different. The working fluids or refrigerants so we can use different refrigerant in the cycle. So for the as a whole cycle, so we can see here is the cooling effect. Okay, is the cooling effect, and here there's work input. Okay, of the high pressure compressor, and there is a work input of the low pressure compressor. There's work input, and so for the cycle, for the then we can see there is definitely we need according to first law of thermodynamics, there is a heat rejection. Okay, there is a heat rejection. So therefore, now we understand the working principle of this two-stage cascade refrigeration technology system. Then let's see how to construct the cycles on the temperature entropy diagram and the pressure enthalpy diagram. So firstly, let's have a look at which state to start. Okay, then we choose state 2. Okay, so for state 2, if the standard vapour-compression refrigeration cycle, we know firstly we need to understand there are 3 important pressures. Okay, there are 3 important pressures. Okay, one is the low pressure evaporator pressure. Okay, so we need to draw the constant pressure line. Okay, so this is the low pressure line, and then there's for the cascade condenser, there is one pressure, and for the high pressure condenser, it also has a constant pressure line or isobaric process. Okay, so similar, in fact, so we can see all processes. Okay, all processes has to be on these three important pressure line. Okay. So we can see all states shall be on those pressure lines. Okay, firstly, let's have a look. For state 2, if the ideal cycle, it shall be dry saturated. So because it's leaving the low pressure evaporator, so it's on the low pressure line. Okay, low pressure line. So it's dry saturated. Then from 2 to 3, so there is a compressor. So we know the function of a compressor is to compress the vapor from the low pressure to high pressure. Okay, then this is an isentropic process for standard one. Then compress it from low pressure to high pressure Okay, then we can define state 2, state 3. State 3 shall be on the intermediate pressure curve line. Okay, then okay, we don't know how to draw because we found so Cascade condenser in the Cascade condenser, these are all okay. We can see this process. This is a heat exchange process. Okay, heat exchange process, and all this four states shall be on the on this pressure line. Okay, this is a heat exchange process, and ideally state 4, 6. Okay, it's dry saturated again, then compressed to high pressure to state 7. For 7 to 8 is a heat rejection process from superheated to saturated vapor to saturated liquid. Okay, then to state 8. So for state 8, it has through the expansion valve. Okay, it will be throttled to state 5. To state 5. And ideally, in fact, for this Cascade condenser, so there is a heat exchange. Okay, so we can see we understand the Cascade condenser is a heat exchanger. So we know the relationship. We can apply the energy equation. So for this open system component, so with the fluid in and out. And then we found it's this is for the high pressure loop. Okay, for the low pressure loop. So we found, in fact, so after heat rejection, our state 4 is liquid is wet saturated to 4, and then throttling process to state 1, and then this is evaporating process. And then we can also draw on our pressure and enthalpy diagram. So we can see all the states on the 3 pressure lines. Okay, and for the in the Cascade condenser, so there is a heat exchange. So apply the energy equation. So we get the relationship as okay. So the change of enthalpy Okay, so in fact, for the correlations between the two high pressure loop and the low pressure loop, so we can get the equation. Okay, so I think we have introduced it. We have introduced it during our this is. Okay, during our lecture, so introducing heat exchanger. So we can consider the Cascade condenser as a heat exchanger. So we can apply energy equation to find out the correlations of their properties. So then we can see to further elaborate the Cascade refrigeration system with the two-stage compression. So this is to further demonstrate it. So this is the low pressure cycle. So this is the evaporator, this is the condenser, and also the Cascade condenser. In fact, we can consider it as a heat exchanger. So it can be served as the evaporator of the high pressure cycle and the low pressure, the condenser of the low pressure loop. Okay. And also we can see the working fluid can be different and the mass flow rate can also be different. So for this Cascade refrigeration system, okay, the working fluids, the refrigerants can be different and the mass flow rate also can be different. So for these two decoupled, I think these two cycles decoupled. Decoupled with each other. It's decoupled with each other. The two-stage Cascade refrigeration cycle is shown here, and the two cycles are connected through the heat exchanger in the middle, okay? And which serves as the evaporator for the topping cycle and the condenser for the bottom cycle. Bottoming cycle is the low pressure cycle. So if we draw the curves on the temperature entropy diagram, so we can see, in fact, if this is a okay, if we we follow the single state. If with the so the blue color, so for single state, compare with the single state. And so let's draw for single state. If single state, okay, so it's here. Okay, I just simply show. So this is for single state. This is for single stage. We can see for single stage, if there's a so the blue lines I want to show you. In fact, it's for single stage. If for single stage, so with a higher compression ratio, so we can see the cooling the cooling effect, the refrigeration capacity will be largely reduced compared with the. So for the original one is so we have is for two-stage the Cascade refrigeration system. So the cycle in blue represents for single-stage compression. So we can say for compare with the single-stage, its advantages. Okay, one we can see there is less decrease in compressor work. So we can see clearly. So then the less compressor work is this shaded area. Okay, this shaded area is the less compressor work. Then for second is with for the Cascade refrigeration system, there is a increase in refrigeration capacity. Okay. So I think basically you need to understand why not only to achieve the compression ratio, we can see if we split single stage compression cycle into multi-stage, just like here, the Cascade refrigeration system, we can see it can largely improve the COP. With a large improvement of COP, so with this Cascade refrigeration system. So now you may get a question about, okay, you feel it's complicated because for this heat exchanger, so you mentioned the working fluids can be different and they are decoupled with each other. So in each cycle, there may be different refrigerants and mass flow rate. Then what about if there is a direct contact heat exchanger? Then we will introduce even it can be better. Okay, it's in engineering practice is more common. So is the we called is with the direct contact Cascade heat exchanger in the two-stage Cascade system. So we can see the heat exchanger is a direct contact heat exchanger. So this one is better. So so for the two-stage Cascade system, I think direct contact Cascade heat exchanger is preferred. So therefore, although for each cycle, for this new one, but the refrigerants has to be same. The same refrigerants, and here there is a direct contact. So later, let's have a look at the design of the direct contact heat exchanger. Also, we have many tutorial problems, in fact, showing us so how we can also apply the energy equation. Okay, apply energy equation to find out the correlations of the refrigerants from the high pressure cycle and the low pressure cycle. So now let's see the main difference between this direct contact Cascade system is the heat exchanger. So it's open or with the direct contact of the refrigerants from the two loops. So there's a direct contact, there's direct heat and mass transfer. So in the direct contact heat exchanger, so the vapor we call is a flash gas or the flash vapor. So the flash gas from the heat exchanger, so we can see this is a flash gas. The flash gas will enter, okay? So we can see, so this heat exchanger, so all the refrigerants are saturated. Saturated mixture of refrigerants. The saturated gas or the flash gas, saturated gas, or saturated gas will, from the heat exchanger, will enters the high pressure compressor intake, okay? And then is compressed to high pressure, okay? Experience condensation, then to state 8, then through throttling to state 5. And then we can see, so because this is a saturated mixture, and the saturated liquid will go to the low temperature thermal reservoir, okay? So the saturated liquid will go to low temperature throttling valve here. Then it's throttled to state 1. So this type of heat exchanger, so we can see it's with direct contact, and then it's a saturated mixture. The saturated gas will go to the high pressure compressor intake for compression, and the saturated liquid will go to the low pressure throttling, low temperature expansion valve. So we can see this type of heat exchanger is more efficient. Okay, just there is a mixing process. So we can see there is a mixing. So for the vapor from the low pressure compressor and the saturated the saturated mixture of state 5, okay, they will mix. There is a mixing process. There is a mixing process. Okay, there is a mixing process. And for this mixing process, it will experience heat exchange. However, the saturated vapor will be sucked by the high pressure compressor, which will be compressed. And the saturated liquid will go to the low pressure expansion valve for throttling process. So this open system can provide some control due to the transit changes in the system by allowing the portion of fluid in each loop alter slightly. So now let's have a look at how we can draw on the temperature entropy diagram and pressure enthalpy diagram. So we can see this heat exchanger. In fact, later we will call it flash chamber. Okay, this heat exchanger is called flash chamber. So no. No, the other is the other type. And also, there is one, so we can see for this one, we also sometimes also call it a flash chamber. So the flash chamber, so we can see is the saturated vapor will be sucked by the high pressure compressor, and the saturated liquid will go to the go to the expansion valve, low pressure expansion valve for throttling. Then we have also the other types of multi-stage compression refrigeration cycle. So besides the flash chamber, however, what's new is here. So we can see there is mixing. Here is the stage 3 is saturated vapor. Okay, here is the same. The saturated liquid will go to the low pressure expansion valve for throttling, so to the evaporator, and the saturated liquid will have a mixing. Okay, there is a mixing of stage 2 and 3 to stage 9. I think now it's difficult for you to understand. However, later we need to know later. So during tutorial session, we have to understand if there is changes of the design of our heat engine. Then we need to understand its working operation and do the calculation. So now we can see there are two mixing process. Okay, one is here. There's a mixing process. Is not mixing, the separation process. Now it becomes separation, and the other is here. This is the mixing process. So for the flash chamber, so we can see for the flash chamber, so we can see the process is here. So if we think here is the mass is okay, then this is following the mass conservation. Okay, for the high pressure cycle, it all has to be mass flow rate 1. Okay, then here if we use mass flow rate 2, then due to mass conservation, here it has to be mass flow rate 2, and here then what's the mass flow rate here? So we can see the relationship between them. So first, let's see the mass flow rate relationship. So from here, we can see for the mass conservation, it shall be mass flow rate 1 equal to mass flow rate 2 plus mass flow rate 3. And then we can see this is a separation process. Then after throttling process is stage 6. Okay, stage 6. Then there is a separation process. For this separation process, so we can see on state 6, there is the saturated mixture then becomes dry saturated vapor will enter into this mixing box, and then the saturated liquid will be throttled by the low pressure expansion valve to state 8. Then let's have a look at the other mixing process. For this mixing process, this is a mixing process. The saturated the dry saturated state 3 and superheated state 2 will be mixing, then get state 9. So how to find out state 2? There is balance. So for this mixing process, it also follow energy equation. So that is the relationship. Therefore, through this equation, we can find out after mixing. So the specific enthalpy of state 9. So therefore, we can define state 9. So for this mixing process. So let's have a look. So for this multi-stage compression refrigeration system, when the fluid used throughout the Cascade refrigeration system is the same, the heat exchanger between the stages can be replaced by a mixing chamber. So this is the flash chamber, since it has better heat transfer characteristics. For this one, instead of its saturated vapor sucked by the high pressure compressor, which was introduced in the previous slide. So here, in fact, there's a mixing process of the saturated vapor and the discharge vapor from the low pressure compressor. So now we can see, in fact, the actual refrigeration system can be very complicated. So with not only we consider the actual refrigeration cycles, just like with the irreversible process, and we have to consider the isentropic efficiency. And in engineering practice, sometimes one single compressor cannot meet with the requirements. So we can see we just have introduced multi-stage vapor compression refrigeration cycles. Then you may ask, I remember, so for our home refrigerator, there are always different scenarios. I think we need to apply our knowledge into different engineering practice. So for the like our home refrigerator, so we remember we have two cooling compartments. Compartments. So we can see for some cases we have different evaporating temperature. To simplify, so we can say, in fact, even like our home refrigerator, we have two evaporating temperature. That means there's two evaporating temperatures. So one evaporators so can be used for food storage, for cooling, food storage. Okay, usually for the compartment the temperatures can be 2 to 4 degree. Okay, for food storage. Okay, keep the food fresh. However, we also need freezing our food, okay, for storage for our freezing food or freezing food, okay. Then we have the other evaporator, like maybe and now we can see, in fact, for actual refrigeration system, sometimes we need multi-stage compressors, and for some cases we may need several. The one compressor may serve different numbers of evaporators, so which can, if there is a requirement for the cooling, the evaporating temperature with a different evaporating temperature. So for the evaporating temperature, so if there is a different expected evaporating temperatures, so we need different evaporators with different evaporating temperature. So for example, this example for our home refrigerator, so we provide a lower temperature for freezing food, and also the compartment for the food storage with the space temperature of 2 to 4 degrees Celsius. So now let's have a look, work on the, have a quick look. I think this part they will be not in our examination. However, you still need to understand the working principle, and no comprehensive question will be in our will show in our final examination. So with the multi-evaporators with one compressor. So for this heat engine, so we can see we have only one compressor, one condenser, but it serves multi-evaporators. So usually the evaporators with different evaporating temperatures. So how to construct the cycles? So we can say, if we look at starting from 3, okay, so then 3, then this is 3 to 4 is compression, isentropic compression process. Then this is a heat rejection process, okay, in the condenser from 4 to 5. Then if we want to achieve different evaporating temperatures, so it's very important for us. We can see there are different expansion valve, throttling valves. With the multi-throttling valves. So we can see for the first throttling valve, okay, so it can throttle the refrigerants to a relatively higher pressure. So because high pressure then means it's a higher evaporating temperature. And then the second, so we can see the second, okay, second throttling valve is to throttle, okay, to a much lower pressure, because much lower pressure with corresponding much lower evaporating temperature. Okay, so we can say if one compressor serves with multiple evaporators with different evaporating temperatures, besides evaporators, we control the achieved evaporating temperature by the throttling valve. Okay, so this is the throttling valve 1. So we throttle to state 6 higher pressure, and if it's throttled to a low pressure, then the evaporating temperature will be lower. So then thereafter, these are same. This is evaporating temperature, evaporating process. Then for the after 6. With the higher evaporating temperature one, we need to further throttle it. Okay, further throttle it. Then the mixing 2 and 8. Okay, is the suction pressure. Okay, I think the pressure 3 is not the low pressure from the low evaporating temperature evaporator. Is this 3 is the mixing. 3 is a mixing. Okay, is a mixing of state 2 and 8. Then state 3 will be sucked into the compressor for compression again. So this is the construction of the cycle of one compressor, one condenser serves with 2 evaporators. So for this one, usually the multi-evaporators can have serves with different evaporating temperature. So we can see how to achieve it besides their multiple evaporators. So the throttling process is very important. So if it's throttled to higher pressure, then the evaporating temperature will be higher. So if it's throttled to the much lower pressure, then its evaporating temperature will be lower. Okay, so this is for the multiple evaporators with one compressors. So in fact, according to our syllabus, we also need to introduce how to control the cooling capacity of our refrigeration system, so which will be introduced so in level 3 subject. To summarize what we have learned today, then is the actual refrigeration cycle. So the ideal one is a Carnot cycle. However, it's not practical, so we have an ideal vapor compression cycle. However, it's difficult to achieve ideal vapor compression cycle. So therefore, we have the actual one. So for the actual one, so there is irreversibility. This way can be superheated. This can be subcooled. And here maybe is we have introduced the efficiency is isentropic efficiency, and also here there is a drop of the pressure due to the friction. So therefore, we understand the actual refrigeration cycle. However, we don't need to worry, because for us, each component are open core system, so we are just using the difference of enthalpy to calculate the heat flow and the work, and also the calculation of the COP. So, and we understand superheating is necessary, and subcooling, in fact, is a desirable effect, has desirable effect. However, if the compression ratio is higher, which means the evaporating temperature is much lower, then we need to split one single compressor into compressors. They can be connected in series. They can be connected in parallel. We mainly introduce in parallel the Cascade refrigeration cycle with with a Cascade condenser or with a flash chamber, okay, with direct contact heat exchanger, and we have to understand they have different presence. And like so even here maybe mixing, I think for us it's very important to understand how the cycle works. So how the refrigerants undergo different thermodynamic process, then we can draw easily so for this mixing process, for this separation process, easily on the temperature entropy diagram and the pressure enthalpy diagram. Okay, we also introduce in some cases, so we may be evaporators cannot meet the needs because we expect different evaporating temperatures. So we expect different refrigeration temperatures. So therefore, we need to design multiple evaporators to meet the client's needs. So how to achieve it? So through the throttling, by the control of throttling process to control the low pressures, okay, to achieve the required evaporating temperature. So I will stop recording now. So I know it's difficult to understand. However, you need to spend time. So after our lecture, okay. So I will stop recording, see if you have any question.